Hello again guys. So in my previous video where I gave an overview of immutable radix trees, I had said that I intended to do a code walkthrough through the library itself, at least cover some of the major pieces, and I want to do that here. So I have already cloned the repository locally, and I have created a playground folder with a file main.go where I think I have written some demo code, and the repository itself has some demo code to help you get started if you just want to mess around with the tree. In my case, I just want to walk through some of the major pieces. So without further ado, I would like to get started. The very first step when you want to create a tree, you create a tree, right? If you want to work with a tree, you create one in the first place. This tree leverages generics. Now, tree has nodes, and the nodes, or rather, the nodes are going to be key value pairs, right? Or rather, the leaves are going to be key value pairs, and yeah, I think I might have explained that, not mentioned that earlier, or maybe I did in the previous video, but a leaf is a key value pair that sets it apart from the examples I showed in the radix tree visualizer. But a node on its own, a node itself, non-leaf node will not have keys or values. It doesn't need to, right? It will only have a prefix. It will have some other fields that are relevant, but it won't have keys and values. So the generics, generic types are relevant because the value is going to be a generic type that the user can decide, right? The key is always going to be a string, but you can see here you're typecasting a string as a byte slice, but the values themselves, they will be generic types that will be decided based on what you choose, right? I won't be going, this code is Golang, this repository is Golang. I won't be going through the code. Quick disclaimer, I'm not great in Golang either, but I know enough to understand important pieces of code. I think if you are interested, you can, and you don't already know Golang, there is a Golang tour provided by the official creators of Golang. It's there on their website. It will give you a quick understanding of Golang in a couple of hours max, and then you can branch out and pursue other resources yourself to get a deeper understanding. But yeah, anyways, I'm deviating already. So this iRadix package, I'll just look into the new implementation. Generic type for our value we have taken as int. If you look at new, it does nothing but return an empty tree, right? So immediately I will go to the tree structure, and a tree has a root node and it has a size, right? This is standard. If you were creating a linked list, instead you would have a head pointer. Similarly, you have a root pointer here, and you have a size, which is the number of nodes. If you look at the node structure itself, it has you have your generic type thing here. You have mutate channels is closed if this node is modified, right? I'm not sure if this is the original comment. This is the original comment. I have prefixed some of the comments I put myself with me. I'm not sure if those are necessary anymore, but I just kept them around. But yeah, and I mentioned this briefly in the slide, right? Mutate channel, it helps us signal mutations, and a node has a leaf node. This might seem a bit weird, but this is how this code base does it, right? If a node is a leaf indeed, then this leaf field will be set appropriately to point to a leaf node. The type struct is right here. If not, the leaf node is just going to be a nil value, right? And since it is a pointer, it can be set to nil, right? And just looking at this leaf node, a leaf also has a channel. I mentioned this in the video as well, because modifying a node is not always the same as modifying a leaf, right? I mean, it's not the same at all, right? And leaf node has keys and values. The key is a byte slice, which is at least it is at least with the examples that I am working with, it's a string. I think I got that wrong just a while ago. It can be a non-string, I guess, because it's a byte slice. You could probably have integers that fit into a byte slice. Not sure if you would need to do that, but you can, right? And yeah, a node is the node itself, the non-leaf, the leaf has the keys and values, but a node itself has a prefix associated with it, right? And that as well. I have covered during the visualization a bit about prefixes and stuff. Now, edges should be stored in order. This represents the edges that branch out from a node, and edges is its own type. It has this generic parameter t, and if you look at edge, it is nothing but a label and a node, right? The label part makes sense. The node refers to the node at the other end, right? This is again pretty straightforward. But yes, a node has multiple edges, can have multiple edges stored in lexicographic order of labels. Yeah, I think those were the structures involved. Going back to new, I am going to create a tree. I'm going to set the root to, I'm going to point the root to a new node, and I'm going to initialize the mutate channel. Right, hopefully I'll be able to explain this correctly. Mutate channels, I'll come to it later, but this new function will return a pointer to my tree, right? That is happening here. Now I'm going to attempt to insert a key value pair rom1, right? So if I go to the insert function, I have mentioned earlier all these modifications happen in the context of a transaction. So the very first step is to create a transaction. Now insert, update, delete, there's no exact update function exposed, but all of these happen in the context of a transaction, right? This is kind of like SQL, where if you specify a SQL query even without using the keywords begin and commit, it is still going to wrap the query in a transaction of its own, right? This is kind of a similar concept, you can think of it. This transaction will not have multiple operations involved, but yeah, it is going to create a transaction nevertheless, right? To prevent all those conflicts and stuff, to allow concurrent readers to operate. Now, if you look at this thing starts a new transaction. If you look at the structure for a transaction has a root node itself. This might not make sense now when you're creating a tree and the tree has a root node. Why does a transaction have a root node? It is because of the whole copy on write concept, because if your transaction has modifications involved, the moment you modify some node, all the nodes on that path from the root to the leaf are modified, including the root, right? So now you have a new root node, and this root node would fit into this root field, right? That is why you have this root field. Snapshot of the root node for use if we have to run the slow notify algorithm. I'm not sure I'll go over this in this video or even subsequent videos. I will not be going over the complete code base, but just to give a little tidbit of information, this has to do with again the channel mutation thing I mentioned in my previous video with the slides. Size once again tracks size of a tree, and this writable cache, I will just read out the explanation. LRU cache, it is a cache of writable nodes that have been created during the course of the transaction. This allows us to reuse the same nodes for further writes and avoid unnecessary copies of nodes that have never been exposed outside the transaction. This will hold only up to default modified cache number of entries. I think this is defined here, 8192. You can read this comment on its own. I will not spend too much time, but yeah, this whole writable thing, I had explained that earlier as well. I think in one of the ending slides, yes, where I had mentioned that copy and write won't happen again. This has to do with that, right? And the reason you keep track of the fact that it should not happen again, the way you ensure it doesn't happen again, is that you put a relevant entry into your writable cache. More on that later. And track channels is used to hold the channels that need to be notified and to signal mutation of the tree. This will only hold up to default modified cache number of entries, after which we will set track overflow flag, which will cause us to use a more expensive algorithm, which is the slow notify algorithm mentioned above. And track mutate, we will not track mutations by default. We will only track them if track mutate is set to true. And I think there is a track mutate function somewhere that allows us to switch our ability to track mutations on or off, right? But yes, a lot of these fields are initialized later when we create a transaction. Only the root, the snap, which is also the root in the beginning, and the size are initialized. I'm not sure I mentioned this earlier. I think I'm getting a bit lost, but yeah, the node and the leaf, both have their mutate channels to signify that, or rather to handle mutations to nodes and leaves. Okay, so this is returning a pointer to a transaction and going back to wherever this was called. I think this was called from insert, right? Yes, you have your transaction now and you're going to attempt an insert against this transaction. You're going to try and insert your key value pairs, and after your insert is successful, you're going to do a commit. So if I look at insert, there's this new root old value and did update, right? So old value and did update will come into play when you're talking about updating an existing node, right? Or updating an existing leaf, updating the value of an existing leaf rather. Yeah, so if you remember, I think I mentioned this in the previous video. So you might, so say you had this tree, and this I can't show values here. I can't show key value pairs. I can just show keys, right? This is how this tree is working, but just imagine it. Say this ROM, which is a leaf node, had the value 10 associated with it. Now I insert another node, which is ROM 20, where my key is ROM and my, okay, I shouldn't have done that, but okay, nothing happened. Okay, so if I try to insert 10, 20, then it will attempt to update ROM. It will try to update the value of ROM from 10 to 20, right? The structure would stay as it is. Again, it will not happen in place. Immutability, copy and write will happen. This root, this all get copied over. Actually, ULIS won't be copied over. You'll have a pointer to that because it's not, this is not the leaf node. I mean, it's on the path in a way, but this is not the leaf node we are concerned with, right? Nodes on the path would be the root node and ROM itself. This, I don't think it would get copied over, right? Actually, yes, it won't get copied over. It's just that this value will be updated after a copy on write, and the root will also have a copy on write involved. So yeah, so old value and did update are involved only when you are updating the value associated with the leaf. If you are inserting something normally, like in this case, you're just inserting ROM1 into an empty tree with just a root or with just a sentinel node, you don't have to worry about this, but this will make sense soon enough, I guess. If you go into the actual implementation of insert, it's a recursive function. This 0 represents a 0 value of your generic type, in our case int, and it is used to return, it's just used when you want to return a 0 value. So we have this length search 0, we have a couple of branches and a couple of conditions and stuff. This is not relevant for our first insert, so I will come back to that later. So now when you want to insert a node into a tree, imagine this, okay, you have to check if the relevant node and the relevant edge exists, right? For example, what I mean by relevant node and relevant edge is, if you wanted to insert ROM, for example, you would have to find the right place where you want to insert ROM, right? And for that, you will check if a node beginning with R already exists, right? A node whose prefix begins with R, or in other words, you can check if an edge with label R already exists, right? The reason you do that is because ROM is going to be inserted under ROM, right? So if just to visualize it again, if I did that, it's coming here, right? So you have to find the right place to insert, which is what this function is doing, get edge, right? And you're searching for the first character. So yeah, actually, if I go into the parameters, if you look at what was passed, if I do insert, I'm passing my root. If you've done binary, if you worked with trees before and you've written recursive code, you usually start from the root. This is standard. You're trying to insert key and value. This is there, but this particular k is it's repeated. So if you look at it, this is the key you're trying to insert. this search is the thing you're trying to search for, right? And the search byte slice is actually manipulated, is actually modified as you descend down the tree. That is why you have two copies, right? Two copies of, that's the reason two copies of k are being passed. One k because this is what you have to insert, one search that is being modified as you descend down the tree. How it's modified, it might be obvious, but if it's not, it will become obvious soon enough. But yes, you have to find the right place for which you get the edge, right? So you search for the first character, right? So in case of inserting Rome, you search, in case of Rome, for instance, you had to search, you search for R to see if there is a node under which you could insert the prefix E, right, to represent Rome. So I get my edge. It's a straightforward function. The reason I get num is because this sorted search function actually needs a size, and I have this function where I just check if the label greater than or equal to label. I won't go into this deeply, but you can read about the search function. You can read about it in a blog as well or something if it's already there. But if you read about it, it should make sense. Basically, it is going to give me the right index of my edge, right? And it is also going to return the node that is attached to the edge. So going back to the edge structure, it has a label and a node. So it is going to return that, right? If it finds the edge, that is. If it doesn't find, it is going to return -1 and nil. So going back, yeah. So in the beginning, when we have an empty tree with just a sentinel root, there is no edge that exists. So in this case, we get a -1 and a nil. So in this particular scenario, our child is nil, which means no edge, create one. Now whatever we're trying to insert is actually, it's going to represent a string in the tree, right? So it is, we also need to create a leaf node, and the way leaf nodes work here, you know that a node has a prefix called leaf, a field called leaf, right? So you're going to create an edge with the label. In this case, we're trying to insert ROM, so our label is R. We are creating a node, we are initializing our mutate channel, we are initializing our leaf. This is all straightforward, and a prefix is search. What we were trying to search for was ROM, right? So we have ROM as prefix, and that's it. Okay, so now the thing is, copy on write is copy all the nodes on the path from the root to the leaf. We have our node and we have our leaf. Now what are the nodes on the path from the root to the leaf, right? We have our root. That root should have a copy on write, right? Yes, a copy on write happens even when the tree is empty and when you have a sentinel node. So if you look at t.write node, it is going to do two things. One, it is going to enable the copy and write, at least to some extent. And the other thing is the mutation tracking and stuff. To some extent it comes into play. It will make more sense if I look at the implementation. There is this comment here, right? Node returns a node to be modified if the current node has already been modified during the course. Yeah, I think there should have been something like this. Yeah, during the course of the transaction, it is used in place, right? Again, this is that last slide or second last slide, right? Not necessary until actual commit happens. This is that point. It corresponds to that. Set for leaf update to true if you are getting a write node to update the leaf, which will set leaf mutation tracking appropriately. So I mentioned this briefly again, that we have two channels, one for node, one for leaf, and updating a leaf is not the same as updating a node. Updating a leaf would be deleting the leaf or updating the value associated with the leaf, right? So in this case, we are not updating a leaf at all. We are just inserting a new node which has a leaf, but it's not the same as updating the leaf. So a for leaf update, if you remember, was we passed false into it, right? Yeah. Now the writable thing I mentioned, it's used to cache all these nodes, right? So it's used to cache the nodes that were copied over because of copy and write, so that in case we have multiple operations, then we can just look into the cache to see if the nodes were copied over, to avoid copying them again, right? So we avoid multiple copy and writes. So this is not actually relevant to single operations like insert, just one insert, one delete. That is what we are doing. We notice we haven't created a transaction like in the last slide where we do multiple operations. So this readable cache, to my understanding, is not really useful in this scenario, but the code is creating it anyways, and it will be relevant if you are creating a transaction and making multiple modifications to the tree, right? But yes, you're creating your cache, you're creating a simple LRU cache. This is simple. So like I mentioned, this thing I will come back to in a bit, but yes, if track mutate, right? Track mutate, there was a track mutate function that can switch track mutate on or off, and we are tracking mutations only when track mutate is true, right? So you can see that we are pushing channel mutate, the mutate channel into we are passing it to track channel, right? And if I go back to our insert function, the n that we are passing is this n, right? And in our case, in the case of inserting ROM here, n is the root node, right? Because we never descended to a subsequent child node. There was no need for it because child was nil in the very beginning, right? So we are copying over our root node. Again, coming back to that, assuming track mutate is nil, we are tracking this channel. I will go to the implementation of track channel in a bit. And if by any chance for leaf update was true and this n which we were trying to copy over is also a leaf, I mean it, or rather it has a leaf associated with it, then we track the mutate channel for the leaf as well. These two lines, it's our way of signaling that mutations happen to this node and to this leaf, right? Or in another way of speaking, that these nodes and these maybe this node was superseded by a new version of a node because of copy on by a new version of the node in a new tree because of the copy on write, right? It's a way of indicating that, it's a way of signaling that. So that's why we are tracking channels, and mark its leaf as being mutated if appropriate. Oh, yeah, I already touched upon this, but this is not a leaf, so we are not tracking the mutate channel just yet for the leaf, although what we're trying to insert is a leaf. That's not involved in the copy on write. Copy the existing node, right? If you have a set for leaf update, so will not I have this comment of mine here, basically replace leaf later if for leaf update is true. You can see this happening in some places in the code. It should be easy to grasp if you read through it carefully. But yeah, we are copying over the node here. Mutate channel, there's nothing in a channel to copy, but we are copying over the leaf. It will be replaced outside if necessary as per this comment of mine. And then if the prefix of the node we are trying to copy over is not nil, then we are copying over the prefix as well. Now our root node does not have a prefix, no need for copying it. Our root node again does not have edges at this point because it is an empty tree, so we are not copying over edges, otherwise we would be, right? And we are copying over edges into this NC node we just created, which I think stands for new child, probably. And yeah, and now mark this node as writable, right? So you are adding it to the LRU cache, right, which is where this becomes relevant, right? If so now again in this case single operation it is not, but like I said, you can have a transaction and you can have multiple modifications, right? And you could without the to avoid multiple copy on writes, you are caching nodes that were copied over in this LRU cache, right? So if this was a transaction with multiple inserts and multiple deletes, you could look into this cache to see if the node was ever copied over before actually copying it over, right? So if it was copied over, you can see you are returning here, but you're also doing this thing where if the node you're trying to mutate, if the node that is being modified, node that is being copied over probably is a leaf node, then you're still trying to track the leaf channel, right? Again, track channel, yeah. So and here you're returning the new child that you created. I'll come back to this track channel in a bit, but I'll just look at right node. Where was the right place? Yeah, this was the place, right? If child is nil, we have no child, we are. In that case, we also have to insert an edge from, in this case, our edge will go from our root node to the newly created node, right? So we are doing nc dot add edge e. Nc will be our copied over root node. We are adding the edge e. It's straightforward. We are doing some stuff here. We are finding the right place to insert the edge because, like I said, edges are sorted lexicographically by the label. and we are appending our edge, but then we are doing some copy over, we are doing some shifting and then putting our edge over here, right? The reason we are appending an edge randomly, blindly in the beginning, despite the sort restriction, is because we are just making room for our new edge in our edge slice, right? And once we have room, we will actually put it into a right place, right? So the way we do that is we shift, we will shift all the edges at index that are already at index to the right by 1, and now because they were shifted over, we can just put our edge in at edge in at index, right? This is straightforward code, and this particular scenario is also straightforward, right? So now let's say that you had ROM, right? So say you have ROM now, because after this operation is done. Now just to maybe make things easier, because I want the root node in my visualization, I also put Tom, right? Just for that sake. Actually, even if you try to insert Tom, something similar would happen. You would come down this path again and you would execute this code, because the edge for T does not exist at this moment. So this code would be executed, right? You would not go here, you would not go here. This is what it would happen, this particular piece, even when you try to insert Tom, right? So I think that covers a big chunk of the insert process. If I look at, if I search for Tom now, right, where is, not Tom, sorry, I don't know why Tom is in my head, but yeah, let me try go to right node, like I promised. I'll go to track channel implementation. Safely attempts to track the given mutation channel, setting the overflow flag if we can no longer track anymore. This limits the amount of state that will accumulate during a transaction, and we have a slower algorithm to switch to if we overflow, right? So this is the slow notified thing. Some of this again will make sense a little later, so hold on. If track notify, basically if we are if we overflow, then we are not tracking channels in this way, so there's no point of going further. We return, right, if track overflow is set to true. If the length of track channels is greater than default modified cache, which is this value, again we set track overflow to true, because we are tracking only a certain number of channels, and we set a track channels to nil and return, right? You can read the comments to understand a bit more, but the idea is we will track only a certain number of channels at a time. In this case, we will track only up to default modified cache channels, right? If there were more mutations that led to the need for more tracking, more channels, then we will fall back to the slow notify algorithm. I'll come back to that later. I think I already repeated that, but yeah. Otherwise, if track channels was nil and it was not initialized when we created the transaction, that is why it should be nil in the beginning at our first attempt to call track channel. So we are initializing it, and then we are actually putting the channel that we want to track, right? So when we inserted ROM, the root node was modified. I mean, it is considered to be modified from the code's perspective because of the copy on right. So the channel for the root node would go here, right? Similarly, a channel for a leaf node can also go here, and this hash map, this track channel map, will keep track of all channels that correspond to modified nodes. Right now, let's go into some other. Okay, wait, that doesn't actually complete insert. My bad, sorry. So we have done this insert, and actually, let me go back to the code. Sorry. So we are returning our NC, right, which will correspond to our newly created root, copied over root. We are returning 0, right, 0 value and false. Like I said, these two fields, these two parameters, they are relevant only when we actually update a leaf, right? And we are not updating a leaf, we just created one. So in that case, old value did update not relevant. New root will be our new root. If it's not nil, then we set our t.root to new root, and now we are pointing to a transaction is pointing to a new tree, right? And if we did not update, then t.size plus plus, this is kind of obvious. If we did not update, then we probably inserted something, right? We definitely inserted something, so we increment the size and we are returning old value and did update. I'm sorry, I'm coming back to this again. I'm not that great in I'm getting confused with the navigation with VS Code. I never tried to learn it properly, but yeah. So we have succeeded. Old and okay, again not relevant, because we didn't do an in play, we didn't do a leaf update, but it's still there, and we are doing a transaction.commit, right? So in a transaction.commit only, this is the first line that's called commit only, straightforward. We are taking the t.root and t.size, and if you remember, both were updated towards the end of the insert function. We are creating a new tree with these two parameters. This will be our new root, this will be our new size. We are setting our LRU cache to nil because we don't need it anymore. We are done with our transaction. Now we don't need to track any further mutations. We are just returning our new tree, right? Returning a pointer to a new tree rather. And now because we were tracking mutations, or we could have been tracking mutations. If we were, we call t.notify. And if again this redundant check is here, or this double check is here, if we are not, return. Otherwise, if track overflow, right, if we exceeded that default modified cache number of channels, we do a slow notify. Else we will loop through the channels, right, loop through that key value, loop through that map, and we are going to close each channel, right? So if you understand channels, and again, even I'm not too good at Golang, I just thought I would explain this code because I understood it pretty well. But yeah, if you close a channel, it's a way of notification, right? And you're setting these to nil because again, you don't need these two anymore. You're done with your transaction. You're done with your notification process. So if you were going to track overflow instead slow notify, it does a complete comparison of the before and after trees. So right, like because of the immutability thing, when you do an insert, you have a new tree, you still have your old tree, and now this algorithm here will actually compare both channels node by node to see if any nodes were modified or any leaves were modified. So it is a little more complicated now. You can still understand it if you read it, but I will not go in that direction. And there is also a test here at line 384 in iRadix_test that again might explain that mutation tracking. You can see here we are creating transactions. We haven't done this in main.go. I'm just inserting directly. But yes, you can create your own transaction. You can enable track mutations, and then we can also delete a prefix, right? We can delete a single key. We can delete a prefix that says delete all keys with this prefix, right? And if not okay, then there is something wrong with our implementation, right? Or rather, there's something, or maybe our tree doesn't have that prefix. I think okay means that. Maybe it means that no error has happened. I'm not sure, actually, I don't remember. But yeah, has any closed mutate channels, right? Transaction was not committed. No channel should have been closed. Okay, actually, wait, this is not what I wanted to show. If one second. Has any closed mutate channel. Transaction was not committed. Okay, right. Sorry, the transaction has not committed. So obviously, no channel would be. Wait, let's just look into this implementation. Okay, you are iterating through to the tree. Wait, add a transaction. Yes. Transaction. Okay, this is what you're doing. Cool. Scans the tree and returns true if there are any closed mutate channels on any nodes or leaves. Okay, yes. So the transaction close. Now I remember. I'm sorry for getting lost. But the transaction close process does not happen until you actually commit, right? And the moment you commit, you see you're doing all these things to see whether the transactions were closed or not, right? If whether the channels were closed or not, right? When a channel is closed, then this line would actually work, right? Basically, case root watch and stuff. I won't explain this further, but you can probably try creating a transaction on your own and trying this, right? You can, if you had a select statement like this and a case with a relevant channel, right? And if this channel was closed, then this particular case would be triggered, right? This is what is happening here. So this is probably a piece of code that enables the channel tracking part and how it might be used. I think there is this database called go-immutable-radix as well that is using immutable radix trees to store data. It is an in-memory database, and I think they're using this. They have this file called watchers where they're trying this. I think they're using channel tracking or something. I'm not too sure. I just briefly looked at that code, or rather a particular file, to maybe identify a good use case of channel tracking. But yeah, I won't go further down that route, right? So I'll just, this is just ignore these actual lines. This was just more like for my testing, and I'm using this as an entry point into the functions which I want to explain. Now say this was a tree and I wanted to insert Romulus. If you understand radix trees, if you looked at my visual, the way I walked through the visualizer in the last video, you know that what would happen is rom is a common prefix with rom. So what ends up happening is you create a leaf node with prefix ulis and you insert it below rom, right? So the first step is in finding if that prefix exists, right? So let's say we go this path, right? Just ignore this. Say we try to insert Romulus. Same old process, create transaction, insert. We will not come here because the search is still not 0. Our search is Romulus, the entire string. Now we try to get the edge. In this case, search 0 will search for R, the edge with label R, and we already have that, right? And the index for this edge is 0, and the child is this rom, right? So we will not end up going through this branch which we went through with rom, which we went through with tom. We come here instead, where we try to find the common prefix between longest prefix between our search and our child dot prefix. Our search is Romulus, our child dot prefix is rom, right? This node with prefix rom, this is our child. So our common prefix is also going to be rom. Just to be clear, what is, okay, longest prefix returns an int, right? So if you have rom, longest prefix returns an int, finds the length of the shared prefix, right? So I think it's going to return 3 for I0, I less than max, or is it going to return 2? Wait, so in this case, max is length k1, which is Romulus, and then we have rom, which is less than max. So max is equal to L, right? So max will be 3 at this point. So we are going from 0 to less than 3, which is 2, and we will end up stopping at 2. So we will be returning 2, I believe, if I'm not wrong. So rom 2, let's say, right, or rather the length is 2, right? Yeah. So if common prefix is equal to the length of the child prefix. So wait, actually in this case 0, 1, 2, length of child prefix would be 3, right? So wait, just let me go back to this implementation. I think it should return 3, not 2. So let's see, we have Romulus and length k1, Romulus, right? Wait, yeah, we are passing Romulus, and then k2 L less than max. Yeah, rom is less than max, so max is 3. 0, 1, 2, yeah, this implementation 0, 1, 2. Actually, let me 0, 1, 2, yeah, got it. Actually, let me do this, right? Let me just put a debugger. Actually, I'm getting a bit confused. Sorry, this should probably not happen when I'm trying to explain stuff. But yeah, my mind is not 100%. But let's see. Let's just debug it, right? We'll debug this code, and when we get here, we'll see the common prefix. So if I go to the next line, sorry, I didn't want to come here, but okay, no, let me go back and just put stuff here. I'm just winging it at this point. Let me debug, go to the next line. Yeah, common prefix is 3, right? I might have missed something, but I still think that implementation is easy. If you go through it, it's a small piece of code, there's nothing complicated there. Yeah, sorry for screwing up, but yeah, if common prefix is 3, 3 is equal to 3 because our child is rom is also 3. So now we exhaust a part of our search prefix, right? Because we know that, like I said before, if you wanted to insert Romulus, rom and rom match. Right now we wanted to we know rom and rom match, so this we are going to descend down from rom onwards. Right now we are going to move to rom and then descend from rom. So now because we are descending from rom, we care about the next relevant prefix, which is ulus. Right, so we are doing this here. Right, we are updating a search, and again we are trying to insert. Right, so in this case, insert, it will try to find our new edge in this case, because our search was updated and our search is now ulus. We will not find that edge. Right, we will not find an edge with label u. So this old thing happens, and this is straightforward. Right, this I have already explained. So we are going to do that. Old value did update, once again not relevant. So if the new child was not nil, which is the case, then in this case n will be this. Right, we will be at rom at this point. Right, we will not be at our root node, because we actually descended one level searching for the right place to insert. So we will do a copy and write for rom. Okay, and in this case nc.edges idx.node is equal to new child. Right, wait, so we are copying over let's say we are copying over rom. We already have the edge, just replace the node. The edge for this, wait, let me get this right. Oh, let's see. Yeah, oh, actually my bad. So we update the search. Our search is ulus. Right, at this point we are still at the root node. Right, because when we got the edge, we skipped this piece of code, we found the prefix, but we are still at the root node. Right, this is actually our first call to insert. So we are not we are still at the root node. When we insert, you can see we are switching to the child. Right, so in this insert function we have descended one level lower. So in the next recursive call, when we come here, we are at rom. We are at rom when we come to this point again, and when we go into this branch. But once that recursive function is done, we come out of that recursive call, we are back at the root node. Right, also in this recursive call for insert, when we are actually going to end up inserting ulus, we already do a copy and write for rom. Right, we will copy and write this, and when we return from there, and when we are at the root, we end up doing another copy and write for the root, and the root node already has an edge to the child rom. Right, so in that case we just point our edge to the new node, new child, which was actually a result of copy and write. Right, and we are returning old value did update, once again not relevant. Right, this covers one particular branch again. Right, now what if we wanted to, let's say we had Romulus. Right, let's just say we inserted Romulus. Yeah, straightforward stuff. Now what if we insert, actually not Romulus, maybe let me delete rom. So this is not relevant. Right, rom gets merged with this child. Now what if I wanted to insert rom? Now in this case, rom as a whole does not match any prefix in this tree. Right, but rom, the first three letters, match with the first three letters of this. So in that case, a node split happens, and now your node is split. This is not green because this is not a leaf. There is no individual string called rom that is a part of the tree, but now we have e and ulus. Right, this particular case is dealt with from this point onwards. Right, so we are writing the node, we are do a copy and write for m. Right, so once again at this point, we should if when we reach this code, we should be at the root node. Right, so if the so in this particular case, the common prefix of when it was rom. Right, let me just delete rom. Yeah, so when we are at rom, our common prefix, whatever its length is, I think the common prefix length is 3. Right, it has to be 3. In this case, our common prefix is not equal to length child prefix, because our child prefix is actually Romulus. So we will not go down this branch. What we do is we are going to do a node split like that visualization just showed you. So for that, first we are going to do copy on write for our root node. Yeah, in this case at least we'll still be at the root node. So I think I had mentioned earlier in a video that because of recursion we will always copy on write from bottom to top, right? That is say always not the case, so I got that wrong. I am sorry about that. So anyways, we are going to copy on write, right, our root node, and now we are going to split our node, right? So we are going to mutate, initialize a new node, and we are going to create our prefix. In this case, the prefix is the common part, the part that is common between Rome and Romulus, right? Common part between Rome and Romulus. I'm not sure. I mean, just think of this as common part. It's a weird way of putting it, but it's Rom, right? So our prefix would be Rom, right? And replace edge would be since we have a new root, we point that edge to our new split node instead, right? So when we so our split node represents ROM, and we will point our root node to ROM, right? And we will go down this path. We will restore the existing child node. So I think the child node at this point was Romulus, right? We will just copy on write Romulus, but except that when you see that we are adding the edge from our split node, which represents Rom, to Romulus, we are changing the prefix, right? Wait, prefix dot prefix, common prefix. Prefix is a byte, so common prefix would be, yeah, common prefix should be Romulus now, right? Should be Ulus. And node mod child, wait, we are creating an edge. Mod child was, yeah, we have done a copy on write for it, so our node will point to a new mod child, and mod child dot prefix is what do I say? Mod child dot prefix is yeah, we are updating the prefix. Yeah, this is our label, my bad, right? So we are getting the label here, which is U. Sorry, I'm getting carried away. And we will update our prefix to be US in this case, right? So this is for Romulus. So again, just to reiterate, Rome, that would happen is Ulus. So at this step, we are dealing with this node. Now we have to deal with this node, right? Node E, which represents Rome. A node with prefix E, which represents Rome, to be very specific. So we create our leaf node. Our key is what we try to insert. So in this case, like I said verbally, we were trying to insert Rome. Value, I haven't really talked about the value here. You know that a leaf is a key value pair of sorts, so we'll not touch upon that aspect. So we insert the leaf node, right? If the new key is a subset, add to this node. Now to explain this, if the new key is a subset, add to this node, right? Basically what happens is, can I come up with an example? Let's delete Rome, sorry. Now we have Romulus. Now what if I try to insert Rom, right? Rom shares, Rom is a prefix of Romulus, but this condition would not be true, right? Length child prefix, because length of child prefix is a lot more than 3. So we would not go down this branch. We are still going down this branch of splitting, right? So what happens, you can say, is it's creating Rom and Romulus. So this is what is happening here, right? So this Ulus part, creating a node Ulus and stuff, should have been taken care of earlier. Also creating the Rom part should have been taken care of earlier. It's just that in this case we are going to turn our copy on written Rom node into a leaf node, right? So that Rom node has a leaf field which was still nil when we did a copy on write on Rom. We just are going to set that leaf field appropriately. So that is what is happening here, right? We are if search is 0, you can try to think of a few examples so it would make sense. And I have this comment here for myself, right? Try inserting Romulus and Rom. And then split node dot leaf, we are setting our leaf. We are still returning 0 and false with our new child. And it should still be the root at this point, I believe. No, would it be the root at this point? Yeah, it would be the root. We would return, right? If we try to insert Romulus, Rom, wait, would it be the root? Actually, no, you can trace the recursive functions. I'm sorry for beating around the bush, but yeah, now we are going to add a edge. We still didn't add, yeah, we are returning at this point. The reason we are adding our edge was the other example I mentioned, where we have Rom, we have Tom, we have Romulus already. Now we have Rome. No, actually, let's yeah, we have Rome here, Romulus, Rome, no, Rome, wait, add edge E, Romania to get here, right? That's what it says. Romulus, Romania. Oh yeah, this is the case of a node split, right? A node split did not actually happen in this scenario. So rather, to go over the examples, we have Romulus and Tom, right? So now if we have Rome, we are going to have this code would have been taken care of by now, this node splitting part. This part of creating a node Ulysses would have been taken care of. The code for creating E would have been taken care of, but attaching a ROM to this new leaf node, this is what is happening here. Once again, guys, sorry for beating around the bush, but yeah, it's just I actually haven't seen this code in a while. So yeah, I'm still kind of I should have probably revised it before coming here, but yeah, this is what is happening. Right, this attaching this node to this E via this edge, that is happening. Yeah, we're creating the edge. You can see that the add edge function is, we already went over that. It's going to find this. All right, so we have covered all the branches of the insert function except for this thing. When can len search be 0? Right, so let's imagine a scenario where, and I think this goes in the direction of updating a leaf. So we have Rom, we have Tom. Now let's assume again, no key value pairs here, but let's assume the value associated with the Rom was 10. What if you try to update that value to Rom 20? Right, in code it will look something like this, right? So you have Rom 10, now you have Tom 2. Now your next function is Rom 15, or let's say 20, right? In this case, what would happen is you would come into this insert function for the very first time. The child for Rom already exists, right? So you will not come here. You will do the common prefix part and you will go down this route, because the length of the prefix, the common prefix is equal to the length of your child prefix. Rom already exists and you're still trying to insert a Rom. So yes, and now when you do this, try advance the prefix, you're left with nothing. You're left with an empty string. So when you do insert now, your search is an empty string, right? It indicates you're trying to update a leaf, right? So in this case, you will insert this branch. Did update is false if you are trying to insert update a node that is already a leaf. In this case, yes, there might be scenarios where you're trying to update a node that is not a leaf. You can try possibilities out, but yes, you are setting your old value to, you're keeping track of that old value that used to be there. In this case, if I'm not wrong, the old value used to be 10, so you're recording that here and you're just saying did update to say that I did an update for my leaf value. Again, a copy on write is involved, right? If I do a t.write node, it's going to come here. And just to remind you, there was this comment earlier. If you have set for leaf update, and in this case, set for leaf update is true, by the way, right? Yeah, it is true because you are updating a leaf. And if you come here, and you see this comment, safe to replace this leaf with another after you get your node for writing, right? Which is what is going to happen. You will copy over your leaf. You will copy over your existing leaf when you are copying over your root node. In this particular example, your root node is being copied over, right? So you're copying that over, sure, but when you go back, let me go back. I mean, this is the old leaf node, right? This is the old leaf node with the value 10. You're still copying that over, but you can see that we are replacing that leaf node over here, right, with the relevant key value. The key is still the same, but the value is new. Now in this case, when you are returning, your new child is still your root, your old value is 10, but your did update is true. And if I go back to insert, yeah, in this case not did update because we updated the leaf value. We are doing a t dot size, we are not doing a t dot size plus plus, no new nodes were added, right? Your tree size did not increase, and that's it, right? And if going back, also this other thing which I might not have mentioned, where is it supposed to be? One second, insert, oh yeah, right node. Yeah, you'll also be tracking your channel for your leaf in this case, right? Because your for leaf update was true. Whether you end up coming here, you won't end up coming here in this case. Like I mentioned, with single operations, the LRU cache is actually kind of irrelevant. But it's there because you might have a transaction with multiple operations batched together, right? You will end up coming here for leaf update. So you're also tracking your leaf mutation channel, right? So your leaf mutate channel. Yeah, I think this covers the insert function. There are other functions, get, delete and stuff, but I think if you understand this much, I think you could actually pursue the implementations of get and delete yourself. I think I did botch up a few explanations a couple of times. I should have revised before I did this, but this is my first attempt. I just wanted to see how it goes. Thanks for your time, and yeah, that's it.